Hello, this lecture is going to be on isotopes and allotropes, a couple of other things. So let's jump in. So we had said prior that not all atoms of the same element, so say coppers or golds or carbons, have the same mass. You can have a carbon with a mass of 11 or a mass of 12 or mass of 13 or mass of 14. It varies depending on which atom you're talking about, how many different variations there are. Those variations are about the number of neutrons in the nucleus. If I'm talking about carbon, there has to be 6 protons, has to. If it's not 6 protons, it's not carbon. So the only thing that I could vary and have it still be a carbon atom is the number of neutrons. And I'm specific about saying atom because if it's an atom, then it has protons and neutrons of the same magnitude. So if I've got 6 protons, I have 6 electrons. So again, the isotope, we're really just talking about varying the number of neutrons. How many neutrons are there? So since chemistry is about the electrons, then changing the number of neutrons in the atom doesn't change the chemistry of the atom. So if you eat some sugar that's got some carbon 12 in it, or 13, or 14, or 11, your body has no idea that that carbon has a different isotopic number. So it really doesn't matter for those purposes, but it does matter under different circumstances. Okay, so if we're talking about isotopes, we're talking about the mass of the particular isotope. So here's a sodium atom. And if I look on the periodic table, I find sodium is element number 11. So that's its atomic number. This atomic number is also the proton number. So whatever your atomic number is your proton number. It's the atomic number because that is the number of protons you have. And we said a minute ago that if we've got 11, if we've got some number of protons and we're talking about an atom, which we are, then I have the same number of electrons. So I've got 11 for my proton number, 11 for my electron number. And it's random, I just chose this, but there are 12 in this isotope of sodium, there are 12 neutrons. Okay, so earlier we had said that the protons and the neutrons have a AMU or atomic mass number of 1, and the electrons don't have a mass number. So if I want to know what the mass of this particular sodium isotope is, the mass would be 23, and that's these two numbers added together. That's it, nothing else to it. So if I move down to this, 15 and 20, that means the atomic mass number of this substance is 35. Well, what substance is it? Well, what has 15 protons? Phosphorus, that's it. So if it's got 15 protons, it also has 15 electrons. Okay, so this is a particular isotope of phosphorus. So now we're going to check the next one. And if it has 92 electrons and it's an atom, that means it's got 92 protons. And anything with 92 protons, that's uranium. And so do these two numbers add up to this number? And they do. 92 and 146 is 238. All right, so Ti is titanium. And if I look on the periodic table, titanium is element number 22. So 22 protons, 22 electrons. And this isotope of titanium is 22, which is 47. Okay. All right, we have another sodium again. So again, sodium has an atomic number of 11. Great. Then I already matched my protons. This one has 11 neutrons. So its total mass is 22. So with these first three, I had said this isotope of sodium or phosphorus or uranium or titanium is. That's because different isotopes exist. So this is a sodium that has 12 neutrons, and this is a sodium that has 11 neutrons. That's it. There isn't anything else to it. The neutron number is different. So that works with any element. Let's talk about the easiest one first. More specific with this. The easiest element is hydrogen. It has 1 proton and 1 electron. And if I look on the periodic table, look at the mass or look at the number underneath the H, it says 1.00795 or something really close to that, depending on which kind of periodic table that you've got. So we're going to need to talk about the oddness of this number and why it's not just a a 1. So if I've got 1 proton, that's an atomic mass unit of 1, and 1 electron is an atomic mass unit of 0. So this thing has a mass, total mass of 1. So this is regular hydrogen. There's another version of hydrogen out there. If it's hydrogen, or you know what, I should also add 0 neutrons. Okay, so there's another version of hydrogen out there with 1 proton. And if it's got 1 proton, it's hydrogen. It's got 1 electron, it's hydrogen. And this one also has 1 neutron. So we're looking at 1 AMU, 0 AMU, and 1 AMU. So I'm going to add the AMUs up. This one has a mass of 2. Okay, so chemically it doesn't mean anything, but it is important as far as the atom itself goes. And the reason this is the easiest one is because there actually is another one, hydrogen, 1 proton, 1 electron, 2 neutrons. So AMU of 1, AMU of 0, and AMU of 2. So this thing has a total mass of 3. Okay, so what I've got is a hydrogen with a mass of 1, that's normal hydrogen, hydrogen with a mass of 2, and hydrogen with a mass of 3. This is a way to write your isotope. So it doesn't matter what atom I'm talking about. Up here, I could have written Ti dash, I would write 47 because its total mass is 47. So this is just a way to write an isotope. This is hydrogen, this is deuterium, and this one is tritium. This one would be called heavy water, and this one here is also a version of heavy water, but it's also radioactive. So the first 2 are not radioactive. Swiss Army, the Swiss Army Knife Company, they also make watches, and they paint the numbers and their dial on their watches. Sometimes they paint it with tritium, with a paint that has tritium in it. So this thing glows in the dark, in the day, it just glows all the time. And it'll glow that way for more than a decade. And you don't need to like hold it up to the light like you do with regular glow in the dark stuff. It just glows because it's radioactive. So the radioactive nature is because this 2 neutrons in this small atom of hydrogen is not stable, and the stability breaks down over time, and it turns itself into something different. It basically just shoots a neutron out with some other extra energy. So the reason I was saying hydrogen is the easiest is because it only has 3 isotopes. If I look at other substances like uranium, there's more than 30 isotopes, but this one just has the 3. All elements will have more than 3 because their nuclei are larger, and so they can accommodate more variations in their neutron number. If I look on the periodic table of elements, we can see that there's this number underneath. So what I mean is this number here, or these numbers down here. And so like this number, this guy right here, or this guy right here. So this is neon, and neon has 10 protons. It has to, because it's neon. And that's what this number is telling us. So if it has 10 protons, it has 10 electrons. And since the total mass is about 20, that means most of the neons that you're going to find have 10 neutrons. Okay. So why is it not 20? If this is 10 and that is 10, how come it's 20.1796 and the parentheses 6 means we think it's 6? That's the variation. We're not 100% sure about that 6 part, but we're pretty close. So why is it like that? This little pie chart is showing you that almost all of the isotopes of neon, all of this portion of the pie chart, have a mass of 20, which means 10 neutrons. There's a few of them that have a mass of 22, which means that has 12 neutrons. And there's another version of it that has 11 neutrons. All right, so what this number down here is, it's a weighted average. Okay, so we know what an average is. So the average of this would be 20 plus 21 plus 22 equals 63. And if I divide that by 3, I get 21. So the average would be 21. But I'm not going to say that the mass of this is 21 because most of the neons out there have a mass of 20. So what you do is you weight it. So another way to think about this is with grades. So if you, sorry, I'm having a cursor issue. There we go. If this quarter you got an A and an A and an A and a C, A's are worth 4 and C's are worth 2. Well, 2 and 4, divide those through and I get 3. Okay, so does that mean my average is a B? No, it's not. But this total amount here is 14. 12 and 2, and so we get 14. What possible amount could I have gotten? I could have gotten 16. So 14 out of 16, and what is that, 3.75? Let me make sure. So that's 0.875. And if I multiply that by 4, I end up with 3.5. So your GPA is a 3.5 because you got more A's than you got C's. So the A's pulled your grade up away from the B average to, I don't know, an A minus or a B plus average. So that's what's going on here. So with the hydrogens, we had a mass of 1 and a mass of 2 and a mass of 3. So is the average of that a 2? Yeah, but it's not a weighted average. Most of the atoms of hydrogen in the universe have a mass of 1. Okay, so the reason that the number is 1.00795 is very few have a mass of 2 and 3, but they do exist. So they bump the number up a little above 1. If I look at sodium, it's 22.9898. So that's really close to 23. And what I know is all sodiums have 11 protons. And if I'm trying to get to a mass of 23, then if I put 12 neutrons in here, that gets me to 23 for a mass. So most sodiums have a mass of 23. And so that means most of them have 12 neutrons to go along with their 11 protons, but not all of them. Some of them only have 11 neutrons, which is why this number is less than 23. Okay, so those are isotopes. That number at the bottom of the periodic table is not a nice round number because the average is weighted for the total possible masses. So some questions you could ask, do these things react differently? And the answer to that is no, because they have the same number. The sodiums will have the same number of electrons, and the electrons are what the chemistry is about. Same thing with the other ones. Can they be separated by chemical means? And the answer to that is no. I can't use any chemistry to separate them because they still have the same number of protons and electrons. And those that electron number is how you do the chemistry. How many isotopes are there? It totally depends. For hydrogen, there's only 3, but for uranium, I said earlier, there's more than 30. Depending on which element we're talking about, the bigger the element is, the more variations you can have. And the masses on the periodic table are nice, not nice whole numbers, because we're talking about a weighted average. And that weighted average deals with, if I've got more of one thing, then it bumps its average up. So since hydrogen has a whole bunch of 1 mass atoms, then this number is really close to 1. So the chances of you, really what this means in this case is the chances of you encountering a 2 or a 3, if you had 1,000 atoms, about 7 or 8 of them would have a mass of 2 or 3. That's where that comes from. Okay, so now we're going to talk about diatomics and allotropes. So if I look on the periodic table, you will find there are elements that are called diatomics. So hydrogen nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There are 7 of them. So this kind of looks like a 7 here, but there's only 6 here, and the 7th one is hydrogen. So if you're talking about what you're breathing oxygen, and people will say O2. And so our atmosphere is 20% O2. Why is it O2 and not just oxygen? So these 7, for the purposes of themselves, their nature is when they're at this temperature of our planet, and at this pressure, the pressure of our planet, they form diatomics, which means they're always found with themselves. So if you get any of these elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine, they will never be by themselves. They will always be paired up with themselves. So a can of hydrogen gas is filled with H2 molecules. A can of oxygen gas is filled with O2 molecules. So we've got a bunch of O2s. O's do not exist. Or H2s. H's can't exist, not at this temperature and pressure. So they form these molecules. And it's just those 7. So not a bunch of things to worry about. But if we're talking about oxygen gas, and you find that in a word problem, you need to make sure that you're thinking about O2, not just O. So this probably helps with something maybe you were curious about before. When I had you write down water molecule being broken apart, and this was what the answer was. And the reason is because these guys can't be by themselves. Some people gave me an answer with just an O there. And the reason that's not a possibility is because this can't exist. So what this means is you actually need 2 water molecules to bust apart so I can get an O2 and a couple of H2s. But we'll talk about that balancing thing a little bit later. Okay, so we've got these 7 atoms that always form diatomics, so moleculars with themselves. And then this allotrope thing is some of the atoms like to form combinations with themselves that are different. Okay, so what kinds of combinations do we have? This is an easy one. Oxygen at this temperature and pressure likes to form O2. We just said that. But if I make it really cold and the pressure really low, they spontaneously reform themselves into an O3. Now, this is really important because this is ozone. This is a toxic gas, and you don't want to breathe it, but we really need this ozone because on our planet, around the exterior of the planet, high up in the stratosphere, is a very thin layer of O3. I gave you a question on the second homework assignment talking about Dr. Molina, and he figured out that chlorofluorocarbons, or molecules that are carbon molecules that have fluorines or chlorines on them, halogens that is, they go up into the upper atmosphere and then they consume the O3. And now if I'm looking at specifically, there is a hole here. And this hole is over Antarctica, and that hole is problematic, sorta. I mean, it's problematic because things down there are not protected from UV, but it's not so problematic because there's not a lot of stuff running around outside on the Antarctica continent. So what is it that the ozone is doing for us, and why would we definitely not want a hole in the ozone layer right above us? Well, oxygen has this interesting way to double bond itself when it's in this O3 form. And so when ultraviolet light comes into the atmosphere, so UV, and we need UV to be blocked because this can cause cancer. What ends up happening is this bond breaks for a moment. Oops. And I've got just an O and an O2. But now the UV has been absorbed. It's gone. It is not going to come down and hit any people. And while this bond got broken, this molecule wants to be put back together. So it literally puts itself back together. It's a self-healing shield, this O3. So that's awesome. We have this shield that protects us from radiation that can cause cancer. And not only does it shield us, but it repairs itself every time it gets absorbed, or every time it absorbs the radiation it needs to absorb. So the problem that Molina found out was if I've got a molecule that's got carbon on it and fluorine or chlorine, and these are refrigerants, when this breaks, sorry, when this guy here breaks, instead of this oxygen going back to where it was, it attaches to this molecule here. And now I've got no O3, it's disappearing. And that's why we've got a hole in the ozone layer. You might ask yourself, why is it over Antarctica? And the reason is something called the Coriolis effect. If you've got a merry-go-round and you put a bucket of water on the merry-go-round and you spin the merry-go-round, the water in the bucket will spin. Actually, it'll spin in the opposite direction. This water, I know it spins in the same direction. This bucket is moving and the water inside of it is not. And then the water inside of it is moving after a certain amount of time. The water has momentum. And then if you stop the merry-go-round, the water in here keeps spinning. So if you've got a bucket of water or you've got some bucket of fluid and you spin it, the sides will end up causing some friction and causing it to go in the same direction. This is why your toilet, when you flush it, it spirals down instead of just falling into the hole. And so this is what happens. The chlorofluorocarbons go up into the atmosphere, and instead of them being where you would expect them to be, which would be over the United States, over Europe, because we use a lot of refrigeration, they get spun down to the bottom of the planet. So the effect turns out to be that Antarctica is sort of the toilet for all of the gases that we put up into the atmosphere. So we're lucky about that because nobody lives there. But if we didn't stop using this stuff, the hole would keep growing and growing and growing and growing until places where people live, like Australia and Argentina, they would end up having no ozone layer over their head. So we've done a decent job of not making these things anymore, although some countries are illegally making these things. So it's still problematic for us. All right, so what were we talking about? We were talking about the fact that an element makes different combinations with itself, and we call those things allotropes. All right, are there any other allotropes? Oh, the answer to that is yes. So here's a good one. This is graphite. This is what's in a mechanical pencil or what's in a regular pencil. It doesn't matter if it's mechanical or not. What I have here are these individual carbon atoms that are hooked up in hexagons. And the hexagon sheets are very strong. But the layers of the sheets barely connect up to each other, which is why that pencil graphite is very brittle. So in a mechanical pencil, it's really easy to break the lead. Even in a regular pencil, it's really easy to break the lead because the sheets do not stick to each other very well. The graphite itself is very strong, but it's hard for it to stick to itself. So when you put the pencil onto the paper and you start dragging it across the paper, if you look at a piece of paper under a microscope, it looks like little mountains and whatnot. And so these mountains scrape these sections of graphite off and they get left behind. So I've got graphite and I've got some graphite and I've got some graphite across the top of this paper. Okay. The next one is diamond. I mean, we obviously know diamond's properties, but this carbon atom, let's say this one right here, it's connected to 4 other carbon atoms. That's important because connected to 4 other things means that this structure is 3-dimensional. This structure here was only 2-dimensional. And across the 2D laterally, this is a very strong structure. But vertically connecting the individual graphite sheets, it's very weak. But since this is the 3-dimensional structure and the carbon atom has something above it and below it behind it and below it off to the side, that this is strong. So strong that diamond is the strongest substance in nature. Another allotrope is this thing called the buckyball. The reason it's called a buckyball is there was an architect named Buckminster Fuller, and he created an architectural design that looks like this, meaning you build a building with this shape. And it looks like a soccer ball. And the reason that he built this shape is this is structurally sound, very structurally sound. So if you built something like out of steel with this building could roll across the ground. You might not want your building to roll across the ground, but what that's saying regardless is that the building itself is very strong. Have any of you seen a structure that looks like this before? This is Epcot Center in Florida, and this has taken this design of Buckminster Fuller, and turned it into a structure. So there's a big old facility inside of there. When Florida goes underwater because of global warming, this thing's just going to roll across Florida and float in the ocean because it's so structurally sound. I've been in one of these before. Well, I've been in Epcot Center, but I've also been in this one here, which is called D1G. It's a naval nuclear facility in Ballston Spa, New York. And inside of there is the back quarter of a ship that was designed to be a testing facility for a nuclear power plant. And so the reason that they put it inside that is because that structure is sound. So if anything were to happen poorly with the nuclear power plant there, that structure would contain it because it's so structurally sound. Again, it doesn't look like the Buckminster Fullerene because they've got it nice and smooth on the outside. But on the inside, there's just these structures that look like this. And this is the same design in a soccer ball. And the reason a soccer ball looks like it does instead of like a basketball, even though it's a lot easier to sew a basketball, is because when you hit one side of this, all of the different stitching points share all of the pressure of the foot. And so the soccer ball lasts a long time because it's distributing the energy all across the soccer ball instead of it just being felt wherever the foot is actually kicking it. So when the chemists found this thing, this C60, they called it a buckyball because they thought it was funny and they thought it would be interesting to name it after this architecture. There is one other allotrope of carbon that you're super familiar with, and that would just be carbon C. That's a solid, and this is charcoal or soot on the inside of, say, a wood stove. This one here, we write it as a C60. Everybody know what that would be. This would be carbon that's in its crystalline form, the diamond, and then this would be carbon that's in its graphite form. All right, that's all I got for isotopes and allotropes. Thank you for watching.